بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Today we will continue talking about complex numbers, and specifically we will talk about set of points. Let's begin talking about set of points in a geometrical approach. A and B are two fixed points and M is a variable point. This is A, this is B, they are fixed as you see, and M is a variable point such that MA is equal to MB. Let's take some positions of M. This is the first position. Notice that MA is equal to MB. This is another position. This is a third position. Now from these positions you're going to see the track where M moves on. We can see from here that M moves somewhere here and it moves on this line. So first we can tell that M moves on a straight line. Now what do we know about this straight line? We can see that MA is equal to MB if and only if M varies on the perpendicular bisector of segment AB. So this line is nothing but the perpendicular bisector of segment AB. Let's see example 1. EFG is a given triangle. When we say that EFG is a given triangle, this means that the 3 points E, F, and G are fixed points. M is a variable point such that MF is equal to MG. The question is to find the set of points M. Now let's specify the fixed points and the variable points. F and G are two fixed points and M is a variable point. MF is equal to MG. This means that M moves on the perpendicular bisector of segment FG. Now let's see the first application. PQ is a given segment. N is a movable point such that NP over NQ is 1. The question is to find the locus of point N. Locus means set of points. Try to do it alone. Let's see the answer. P and Q are fixed points. N is a variable point. NP is equal to NQ from here, from this relation, so we can tell that N moves on the perpendicular bisector of segment PQ. Now let's see the second case. MA is equal to K. A is a fixed point and M is a variable point. K is an arbitrary strictly positive real number. In other words, K is a constant which is strictly positive. Now this is A, and we know that MA is equal to a certain constant. Let's say it's equal to 2, 3, 5, whatever. This is K in my figure. This is the first position of point M. Let's take another position. This also could be the position of point M such that MA is equal to K. This is a third one. So from here we can tell that M moves on a certain circle. So MA equals to K if and only if M varies on the circle with center A and radius K. Let's see the second example. EF is a given segment. M is a variable point such that EM is radical 5. The question is, find the line on which the point M varies. So we need to find the set of points M. Let's specify the fixed and variable points. E is fixed and M is variable. EM is radical 5, so applying this property we can tell that M moves on the circle with center E, the fixed point, and radius radical 5, which is the constant. Now let's see the second application. ABC is a given triangle. M is a variable point such that AM is equal to BC. And the question is find the trajectory on which the point M varies. Try to do it alone. Again, A is fixed and M is variable. AM is equal to BC and BC in this case is a constant. Then M moves on the circle with center A and radius BC. Now notice here that BC is a constant because B and C are fixed points and BC is nothing but the distance between them. Let's see the third case and the last case in the geometrical approach. If angle A and B is 90, A and B are two fixed points and M is a variable point. So this is A, this is B. M is a variable point such that angle A and B is a 90-degree angle. Let's take some positions of M. This could be one of the positions of M. In this case, notice that angle A and B is a right angle. This could be another position. This is a third one. So we can also tell from here that M moves on such a circle. So A and B is 90 degree if and only if M varies on the circle with diameter AB deprived of points A and B. Deprived here means excluding points A and B, because if M is located on either A or B, angle A and B would not be a 90-degree angle anymore. Example 3. CD is a given segment. M is a variable point such that MC is perpendicular to MD, and the question is to find the locus of point M. Now, what do we mean by MC is perpendicular to MD? This means that angle CMD is 90. Let's specify the fixed and variable points. C and D are fixed, M is variable. Now, MC is perpendicular to MD means that angle CMD is 90. So where does M move? It moves on the circle with diameter CD deprived of C and D. Let's see the application. PQ is a given segment. M is a variable point such that the triangle MPQ is right at M. And the question is to find the locus or set of points M. Try to do it alone. Let's see. P and Q are fixed. M is a variable point. The relation PMQ is 90 because the triangle MPQ is right at M. So we can say from here that M moves on the circle with diameter PQ deprived of the 2 points P and Q. Now let's see the second part of that chapter, which is set of points but in an analytical approach. Let's see what do we mean by this part. The plane is referred to a direct orthonormal system. We have a variable point M, x, y. M varies on a straight line if and only if y equals ax plus b, and we know this from before because an equation like y equals ax plus b represents a straight line. Now specifically, M varies on the x-axis or the abscissa axis if and only if y is equal to 0, and this is an equation of the x-axis. And M varies on the y-axis or the ordinate axis if and only if x is equal to 0, and this is an equation of the y-axis. And the second part, M varies on a circle with center A, AB, and radius R if and only if x minus a quantity squared plus y minus b quantity squared is equal to r squared. So we know from before that such an equation represents a circle and such an equation represents a straight line. Let's see this example that clarifies the idea. The plane is referred to a direct orthonormal system MXY, and the question is to find the set of points M in each of the cases below. The first case, remember, you have to ask yourselves the question, is this an equation of a line or a circle? And we know from here that y is minus 2x plus 4, which is a line. So M varies on the line with the equation y equals minus 2x plus 4. As easy as you see. The second part, this equation, we try to reorganize it. So we get x equals 0, so we can tell that M moves on the ordinate axis. The third case, remember here, as we said before, this is the general equation of a circle with center AB and radius capital R. So in this case, M would move on the circle with center O 0, 0, because small a and small b in this case are zeros, and radius the square root of 25, which is 5. Now this case, this is also direct. So M moves on the circle with center 1, negative 3, and radius 4. Pay attention here. we must have a minus, and because we have a plus, we write here negative 3. Now what do we do if the circle is given in an expanded form? Let's see, first we organize x's alone, y's alone. Then, look here please, then we complete the square, and if we want to complete a square like x squared plus bx plus c, we have to add then subtract b over 2 quantity squared. So in this case we have x squared plus 2x, we add and subtract 2 over 2 quantity squared, which is 1. As you see here, we added 1 and subtracted 1. And for the second case, we add and subtract negative 4 over 2 quantity squared, which is 4. This is where we added and subtracted 4 and minus 11. Then we try to complete the square. The first three terms give x plus 1 quantity squared. Now y squared minus 4y plus 4 gives y minus 2 quantity squared, and the constants, which are negative 11, negative 4, and negative 1, they sum up to 16 after the equal sign. And this would be an equation of a circle whose center is negative 1, 2, and radius 4. Last example, if we have such a circle, remember, if we have x squared and y squared and the coefficients are equal, this could be an equation of a circle. Now here, because the coefficients of x squared and y squared are 2, the first step is to divide by 2. In order to apply a procedure like the one given in part E, we must have x squared and y squared. We cannot have coefficients other than 1. So in this case, we divide by 2, we get x squared plus y squared minus 6x is 0. Then we repeat what we did in part E. In other words, we reorganize x's alone and y's alone. We complete the square, so we add and subtract negative 6 divided by 2 quantity squared, which is 9. So the first three terms lead to x minus 3 quantity squared, y squared, that's it, and then negative 9 becomes positive 9 after the equal sign. And this represents a circle with center 3, 0 and radius 3. Now let's see the application. We need to find the set of points M in the first case. Try to do it alone. So this would be a straight line whose equation is y equals half x plus 2.5. The second case, try also to do it alone. We reorganize it, we get y equals negative 1, so M moves on a straight line with equation y equals negative 1. The third case, try also to do it alone. Now here the set of points M is phi because a radius cannot be negative. The fourth case, so in this case M moves on the circle with center L negative 2, 0 and radius 3. Remember, if we have a square on x, a square on y, and the coefficients of x squared and y squared are equal, this could be a circle. This case, so in this case we reorganize x's alone, y's alone. We add and subtract to complete the square. So here we add the coefficient of x, which is 1 divided by 2 quantity squared. So we add and subtract 1 over 4. And then the coefficient of y divided by 2 quantity squared, which is 9 over 4. Then the first three terms lead to x plus half squared. Y squared plus 3y plus 9 over 4 leads to y plus 3 over 2 quantity squared, and the constants lead to 10 over 4. So M varies on the circle with center minus half minus 3 over 2 and radius the square root of this constant, which is the square root of 10 over 2. Now the last application, try also to do it alone. So if we divide by negative 3, we get x squared plus y squared minus 4x minus 1 is 0. Reorganize, complete the square, we get this quantity. So M moves on the circle with center 2, 0 and radius radical 5. Now let's see the fifth application. A is a fixed point whose coordinates are -1, 0. M is a variable point, and M prime is also a variable point such that we have a relation between x prime, y prime, x and y, which is represented here. Now we need to find the set of points M when x prime is 0. Try to do it alone. Now x prime is 0 means that x plus y minus 1 is 0, and x plus 1 squared plus y squared is never 0, so here we have two conditions. The first condition leads to the straight line whose equation is y equals minus x plus 1, and the second one, remember here, if this quantity is equal to 0, so x would be -1 and y would be 0, so these are represented by the coordinates of point A. So we come and say that M moves on the straight line whose equation is y equals minus x plus 1 deprived of point A, and here we excluded point A because we have here doesn't equal. Now let's see the second case. Y prime is 2 and we need to find the set of points M. Try to do it alone. This is y prime, remember. So y prime is 2, then this quantity is going to be equal to 2 and the denominator should never be 0. If we simplify the first quantity, we get such an equation. So if we add and subtract and reorganize it, we get such a circle. So we can say that M moves on the circle with center -2, -1 and radius radical 3 deprived of point A, and remember this deprived is given from this condition. Now the third part, try also to do it alone. Let's see. If M prime moves on this line means that y prime is minus 2x prime, and if we replace, we get such a relation, and this relation after simplification becomes like this. We simplify it more to get this expression. We reorganize x's alone, y's alone, we add and subtract to complete the square, and finally we get such a relation. And this represents a circle whose center is -1, 0 and radius is radical 3, and don't forget to exclude point A. Thank you.